Hey, Katie. Is it going? We're back. So, hope you enjoyed your retreat. You all were on retreat with her, some of you, aren't you? All right, awesome. Okay, so to recap a little bit, so second part of chapter 6, implicit differentiation. So again, all of these equations are equations that we know how to take the derivative of, or we could, on this last one, solve for y and take the derivative. But they're all examples of what we would call dy dx, where we're taking the derivative of y with respect to x, right? Because x is the independent variable. Okay, so these we can all say that y is given explicitly in terms of x, or we could easily get y by itself. So sometimes that's not the case, and we still want to take a derivative, dy dx, and we have to use implicit differentiation. So implicit differentiation is when y is kind of more intermixed in the equation, right? And it would be harder to get it by itself. So y is said to be given implicitly in terms of x, all right? So it just kind of means that the equation really using both the variables, not just like a y function using x, okay? And when we've got these types of equations, we have to use what we call implicit differentiation. And we're going to use this symbol a lot, the dy dx. And it takes on a little bit more of a meaning here, okay? It still means a derivative of some type, but you'll see it means it takes a little bit different connotation. So when we're using implicit differentiation, we're still going to, all of our derivative rules still apply. So we're still going to take the derivative of every term with respect to x, but we're going to be doing it on both sides of the equation now. Okay, so on the left side and the right side. If the term is a constant, like just a number, or just has the x variable, all the same rules apply. Okay, so that part hasn't changed. But when a term has a y in it, you want to think of that y representing some function of x. Even though it's just a variable, it represents some kind of function of x. And we're going to use dy dx to denote its derivative, okay, using the chain rule. So again, we're going to use a lot of examples of this to show this a little bit more clearly. But one way to think about it, if we look at this function right here, okay, there's no y here, but how do we use the chain rule to take it further? What do we do? Bring the 2 down, and then keep the parentheses the same. Subtract 1, and then what comes next? The derivative of what? Of the inside, right? Which would be a 4. Okay. Then we could continue cleaning that up, but I'm going to leave it right here for now. So we basically took the derivative like this was just one big variable, right? Like we brought the 2 down, subtracted 1, then the derivative of the inside. So when we have a function that has a y in it, we're going to kind of do the same kind of process. We're going to take the derivative of just y. So for instance, with y squared, we take the derivative of y squared, which would be 2y, right? And then subtract 1 from the exponent, give it a 1. But then to represent like the derivative of the inside, to represent the derivative of the y part, we're just going to write dy dx. Okay? So every time we take a derivative of y, again, because it represents some function of x, we use a version of the chain rule, or really we just take the derivative of that y, and then to represent like the derivative of the inside, we just plopped in a dy dx. Okay? Now, after we do that, if the term has a combination of x and y, we're going to have to use the product rule. It could be multiplied or quotient if they're going to be divided. Again, we'll go through examples. And then at the very end, we isolate and solve for dy dx. Okay? So we put these in our equation anywhere we see a y, but in the end, to actually answer the problem or to solve the derivative, we solve for dy dx. Okay, so a little bit weird, a little bit strange, a little different. Okay, so let's try a couple of these. Okay, so again, when the term has no y in it, all the same rules apply, right? So if I want to take the derivative of 5x to the third, that would be 15x squared, right? And then on 4y squared, I take the derivative just like it's an x, so that would be 8y. And then I have to denote the derivative of the y, so I say dy dx equals the derivative of 10 would be what? 0. Nope, that's step 1. Step 2 now is what I highlighted right here. Now we want to get the dy dx by itself. That becomes our answer, okay? So to get that by itself, what do we want to do? Hi, Nellie. Good question. Right, and it does, and these do get multiplied. And the reason, again, the best explanation I can say is that this y, we don't really know what y stands for exactly, but it's some function of x. And because we're taking the derivative with respect to x, whenever we take the derivative of the y, we just take the derivative and then tack on the multiplied dy dx. Okay? Because it represents some kind of function of x that's not clear. So it's implicit, so we just implicitly represent that with the dy dx. Okay, so I'm sorry I don't have a better explanation, but what we're doing here is we're actually solving for the derivative of y represented by dy dx. Okay? All right. So yeah, it just adds a whole kind of another layer of complexity that I don't do a really good job in explaining. Okay? All right. So to get that dy dx by itself, what do we want to do? Subtract 15x squared. So we get 8y dy dx, and we get negative 15x squared. And then to get that completely by itself, we do what? Divide by 8y. And actually, the meaning of implicit differentiation gets a little bit more clear as we will do some applications with these next chapter, and it kind of gives us a little bit more meaning. But it doesn't really quite explain how the math, why this works, but it kind of tells you what we're finding with it. So final answer, dy dx equals negative 15x squared over 8y. No, why don't you just give up? But thanks for asking. Okay, questions about that? That's the answer, yes. Yes. Yeah, and that's what's kind of tough about these, is they're not pretty answers. Like they don't come down, we're actually right, our answers actually look like functions, right, still? So they're not pretty pat answers at the moment. We get a little bit better when we do some related rates with them later on. Okay? All right, let's try another one. Okay, so here again, terms without a y are the same. So 7x squared becomes 14x minus 4x squared, 4y squared becomes 8y. But again, we need to show the derivative of the y, so dy dx equals 0. Don't forget that it equals 0. Just remember that derivative of a constant is just 0. Now, to get the dy dx by itself, we're going to subtract 14x. And now we divide, right, by negative 8y. So we get negative 14x over negative 8y. Now, again, we do want to simplify as much as we can. So what can we do to that? Positive, what? 7x over, taking out 2, 7x over 4y. That makes sense? No, but the problems get a lot harder. Well, because next what we're going to do quotient, we're going to have like a 4x1 squared. So we have to do product rule, we have to do quotient rule. It gets more exciting. Is it just the same thing as well, I mean, it is just all it is, but be careful. Like, just bear with me. It definitely gets more complicated than what we're doing right now. But the steps don't really change. The problems just get more complicated. Catherine. Yes, if this were just like, and we're going to look at one right here. If this were just negative 4y, then the derivative of negative 4y would just be negative 4, but we would still have the dy dx to represent the derivative of what's inside. Okay? All right. So that's, and actually, I think that's, actually, you guys go ahead and try this one on your own. It won't always be like that. But the dy dx just represents the derivative of y with respect to x. So you guys go ahead and try this one. Oh, that's right. Okay, yeah, let's do this one together. I looked at that and then I thought that maybe it was the reason yesterday that I didn't want them to do that extra time. So yeah, thanks. Let's do that together. Okay, so again, we take the derivative, so we get 9x squared, right? And then minus 16y dy dx. Everybody with me? What's that? Oh. And then equals, so 10y, so again, the derivative of 10y would be 10, but then again, it's the y, so we have dy dx. Okay, so now in order to isolate the dy dx, what's our method? How are we going to be able to get this by itself? Add 16, so then we get them both over here, and then what? No, we're not going to be able to add them. Well, we're going to take out the dy dx, right? A GCF? Okay, let's try it. So first, let's get all the dy dx terms together. So we get 9x squared equals 10 dy dx plus 16y dy dx. Yeah, and be careful, because even though they both have dy dx, we can't combine 10 and 16y. If it was 10y, we could, right? 10y plus 16y, we can make 26y. But with this one, so to combine terms, they have to have the exact same variables to the exact same power, right? So these cannot be combined, but what we can do is take out a GCF of dy dx. Does that make sense to everybody? Okay. And now how would we get dy dx by itself? Divide by 10 plus 16y. Now, could that be simplified at all? No. Okay, questions about that? All right. Now, let's try one where we have a term that has x and y both inside, right? So we're going to take this one, normal, 5y squared. We know how to do that. This one, we're going to have 4xy. We're going to have to look at that as product rule, like two functions, like 4x is going to be a function and the y is going to be a function. Okay, so let's see what that looks like. So we get 14x equals 10y dy dx plus, so now we look at 4x as a function and just y as a function. Okay, so what is the product rule? Derivative of the first times just the second, normal, right? And then plus derivative of the second times just the normal first function, right? So this is the only place in the product rule or the function rule, this is the only time where you will ever write a y without a dy dx, okay? So when we do the first part of this product rule, it is the derivative of the first. So what's the derivative of 4x? 4. And then it's just times the second function. So the second function is just a y. So since we're not taking the derivative of the second function, we're just writing a y by itself. And that's the only time you're ever really going to write a y without a dy dx next to it. Okay? And plus the derivative of the second. So what's the derivative of y? 1 dy dx, right? And you don't have to write that one. I always do just because when I'm going through it in my head, I first pass through. So it's derivative of the second times the first, so times 4x. Okay, and then plus 0, right? Okay? Very good? Okay, so the way, anytime I have to do the product rule, though, I do like to write it like this, where I just write it in exactly the way I say it, right? Derivative of the first times the second plus derivative of the second times the first. Now, this term, though, is really a 1 times a dy dx times a 4x. So we can actually write that term as just 4x dy dx. Does that make sense to everybody? Okay, so I'm going to go ahead and, okay. Okay, so that's what we have, right? So all I've done here is I've really just rewritten it and combined all of it here. So now I have to get the dy dx by itself. So what do I want to do? Not yet. I want to subtract, yeah, just the 4y, right? So I get 14x minus 4y equals 10y dy dx plus 4x. X. And now what do I do? Take it out, right? So get 10y plus 4x. Now to get it completely by itself, I divide, right? So my final answer, well, not my final, but dy dx equals 14x minus 4y over 10. I'm going to write it in order 4x plus 10y. Now, could I reduce that at all? What could I do, Kevin? I can divide by 2. So I'm going to show you the right way to do it. A lot of you, and I don't take off for it, it's okay if it works, but a lot of you would just start slashing, you know, by 2, okay? Just be careful about that, because if this were like a 5 and everything else was the same, you couldn't do that, okay? So the best way to make sure you can reduce by a number is to actually like write it as a GCF. So what I'm basically doing up here is up here I want to take out a 2, and I get that. On the bottom, I want to take out a 2. And then I can cancel those 2's, Okay, so just be sure when you reduce by a GCF like that, that you are taking out everything, that it can come out of everything. Do you have a question, Reese? You not liking this? Oh, okay. That's okay. I think I can handle that. Okay. Everybody good? Can we cancel out these x's or the y's? No, right? Because again, they're being added and subtracted with other terms. So just like any rational expression, you can't do that. Okay. Now, the one thing I will say about these, if you had decided, well, actually, I'll talk about that later. It doesn't really apply to this one. Okay, let's. Do you all want to try this next one on your own? No. Okay. All right. Well, let's do it this way then. Oh, you want to do it yourself? Okay. You guys, I tell you what, I will do it silently up here. I actually do. If I get one of those. Okay, so here again, if you just took out a 2, you end up with this answer. If you took out a -2, I just did that, you got that answer. Okay, now the one thing that I want to say about this, up here, if you had decided at this point, I decided to take my non-dy dx terms over to the right. You could have taken these over to the right instead. And what would happen is you would have gotten the exact opposite of signs up here. So this would have been 2. Did anyone do that? Did you get 6x plus 2y over -4 minus 2x? You did, okay. And that's perfectly fine, okay? As long as every single sign is the exact opposite, it's an equivalent answer, okay? So just be aware of that, like if you're checking in the book or when we check homework and stuff, okay? All right, everybody good? We're getting the hang of it? All right. Let's get things a little bit more complicated with fractional exponents, okay? All right, so first let's rewrite this. So we get 4x to the 1/2 minus 8y to the 1/2 equals 6y to the 3/2. Well, I haven't done any derivatives yet. All I did was rewrite those, right? Okay. All right, so what's the derivative of 4x to the 1/2? 2x to the what? To the what? Right, 2x to the -1/2. Everybody good with that one? And what's the derivative of -8y to the 1/2? So tell me what to write. Negative for y to the, and then dy dx. Okay. And then 6y to the 3/2 gives me what? 9y to the 1/2, and then dy dx. Okay, everybody good? All right, what do we do next? Kendall, what do you think? Well, yes, we are, but let's do that together with, we need to move something around. Right, exactly. Good way to put it. Okay, so when we do that, we'll go ahead and bring stuff down too. So we're going to add 4y to the -1/2 to both sides. So I get 2 over x to the 1/2 equals, if you all are okay, I'm going to go ahead and pull out my dy dx at this point. Are you all good with that? Dy dx. And I get 9y to the 1/2 plus 4 over y to the 1/2. I agree with that? Anybody see a problem? What's our next move then? What are we going to do next? Then divide. Can we divide this? All right. Because this is really still an expression, right? This has got like an equation. So we really can't divide this and then like do keep, change, flip, because this is not one term, right? So what do we have to do? Common denominator, right? Okay, because again, think about this as that's really over 1, right? So we need to, in order to make this one term, we need to get a common denominator. Then when we divide, we can change, flip, and it all becomes just one fraction, right? So what is our common denominator going to be? Y to the 1/2, right? Everybody good with that? What do we need to do to this term to make it have a denominator of Y to the 1/2? There you go. And what do we get? Right. 9y to the first. Everybody get that? Again, we're basically multiplying y to the 1/2 top and bottom, right, to make it be this fraction. And y to the 1/2 times y to the 1/2, you add exponent, you get y to the 1. What do I put over here? Plus 4, y. Let's see. Exactly. It already has that denominator. You will have to do this a lot, so make sure you get it. Okay. So now we can divide and we can do a keep, change, flip, right? Another way you can think about it, we can do the keep, change, flip, but the other thing you're doing is you're really just multiplying by the reciprocal. Does that make sense? Okay, so we're really multiplying by y to the 1/2 over 9y plus 4, y to the 1/2 over 9y plus 4. Okay? So our final answer is actually 2 over x to the 1/2 times y to the 1/2 over 9y plus 4. So we get 2 y to the 1/2 over, and I prefer that, well, you really do not have to distribute that x to the 1/2 inside. It really just kind of opens you up for errors there. It's easier just to keep it on the outside. I wouldn't take off if you did distribute it, but it's just as easy to keep it out. Okay, questions about that? What do you mean? Oh, so I did this, this is the one I divided by this. I had to get that one by itself. I had to get the y diff by itself. So I'm dividing by this. So it's keep, change. So I kept this the same. I changed it from division to multiplication. And I flipped this. Again, that is why it's almost easier. I know we always do the keep, change, flip stuff, but it's the equivalent of multiplying by the reciprocal over here. And that kind of takes a step out of it, if you will. So okay, don't think I'm doing this all twice. This is just one kind of more straightforward way to think about it. If I see that where I'm just multiplying by the reciprocal, and I end up with the same answer. Okay? That's one way to do it. Okay. Questions about that? All right. I feel like I'm going kind of fast on this. You all with me? All right. Okay, let's try another one. Okay, so what are we going to do on this side? Quotient rule, right? So 2y squared becomes 4y dy dx. And what do I do on the right side then? So what's the quotient rule is what? Derivative of the top Beautiful. So what is the derivative of the top? 1. And then times 5 minus x minus, what's the derivative of the bottom? What kind of one? Negative 1. Times the top, 5 plus x, over 5 minus x squared. So we can keep the 4y dy dx. We can keep the 5 minus x squared. What happens to the top? It becomes what? 5 minus x stays. And then minus a negative 1 becomes a plus 5 plus x. 10. Right, so the x's go away, right, in the denominator, or the numerator, sorry. So we get 4y dy dx equals 10 over 5 minus x squared. What's that? Oh, okay. You're just asking what? Oh, I think you're good. All right, now what do we do? Divide by 4y. And there again, one way to think about that is we're actually multiplying by 1 over 4y. This is just kind of easier way to think about it. It's the same thing as dividing by 4y. Is everybody good on that? This is just kind of a shortcut way to think about it. So so if I thought about it like 4y over 1, I'm multiplying by all this simple. Just keep it right, write it down and keep it flip. We're really just flipping the fraction so it cancels out over here. And we get dy dx equals 10 over 4y 5 minus x squared. And now I had said it was kind of optional, not to distribute the previous example, but you could. Anytime you have a quantity or a parentheses with a higher power, you can't distribute into that, right? Because that would be, you would be giving yourself more 4y's than you had planned, right? So anytime you have a power that you can't distribute into, but what can we do to that? What can we do for 10? 10 and the 4, what can we reduce that by? Divide both by 2, right? So we get the final answer would be 5 over 2y 5 minus x squared. Okay, fun. Not too bad. I mean, some different beats word problems, right? No? Yeah. Okay. All right, let's try another one. This one gets a little bit trickier. This one's a little bit trickier. Why? What's going to happen on this one? Because the y is are in the function, right? So that This gets a little bit, yeah. Okay, so 4x squared, we just get 8x, right? All right, now what's the derivative of the top? 1 what? 1 dy dx times 2 minus y, just a y, right, because we're not taking the derivative of the bottom, minus derivative of the bottom is negative 1 dy dx times the top, and then all over the bottom squared, which is no derivative. Yeah, so we're good. Okay. So actually, this doesn't turn out too bad. So we get 8x. Let's see how we're going to do this. So we get 8x times, well, let's, okay, we could, all of this has dy dx. You all agree with that? So we could go ahead and take out the dy dx. Does that make sense to everybody? So if we went ahead and wrote this as dy dx, boom. Okay. Then inside we have the 2 minus y. And then we have, again, negative times negative equals a positive 2 plus y. That makes sense? Otherwise, we would have distributed that in like negative 2 dy dx, negative y dy dx, and, just and then distribute it. So this becomes positive 2 plus y. So we end up with 8x equals dy dx. Yeah, and just a 4, right, over 2 minus y squared. So you do want to make sure that dy dx really only applies up to that 4. So how do we get the dy dx by itself? What's that? Right, yes. Or again, or we could multiply by the reciprocal over here. And those all cancel. So we get dy dx equals 8x 2 minus y squared over 4. And then what can we do to that? Right, 8 and the 4 becomes 2. So we could, actually that simplifies nicely. So it just becomes 2x 2 minus y squared. Okay, questions about that? You want to try that next one by yourself? No? Okay. All right, last one. We can do it, right? I think it's the last one. You have already gotten farther than A block did, but okay. All right. Y'all don't talk near as much as A block. This one's going to be a little tricky. Okay, well, kind of. We'll see. There's going to be one thing we're going to end up with a negative x. Okay, so, but x squared y to the third. Who can tell me, so what are we going to have to use for that? Product rule. So, somebody want to tell me what to write? Go ahead, Grace. Well, what are we missing here? dy dx, and then times x squared. So again, I'm going to eventually rewrite this all together, but I like to write it exactly how I'm thinking it, with the rules. So derivative of the second is 3y squared dy dx times the first, okay? And then minus what? 3 halves x to the negative 1/2 equals, you can tell me what to write on this side. 10y dy dx. There you go, right? So this is the most crucial step, right? So don't try to do too much on this step. Like don't try to, bring stuff down or, just get this step right and then we start simplifying it, right? So what do we need to do next? Minus. Why was minus? Oh, I know you did minus 3. Yeah, let's subtract it and write it all together, right? Oh, yeah. So we're going to actually subtract, and we can write that now as 3x squared y squared dy dx. So we get 2x y to the third. And I'm going to go ahead and bring that x to the 1/2 down. Equals, and I'm going to go ahead and take out my dy dx. 10 minus 3x. All right, that's not bad. If I agree with that. But what's our problem now? Over here, right? Because when we divide, we need a common denominator over here, right? So what's that common denominator going to be? 2x to the 1/2. Did I mess up? Minus 3. Okay. Everybody good with that? Everybody agree? Okay. Okay, so when I want to rewrite this term, I can keep my negative 3, right? Because this stays. What is this become? It's not our term become. This is 4. X to the 1/2 times x gives me x to the 3/2 y to the third. Come on, you all can do this. Okay, 2 times 2 is 4, right? X to the 1/2 times x to the first becomes x to the 3/2 and y to the third. That's not that bad. What's that? Okay. Where did I lose y'all? What did I do? Oh, okay. So, all right. So, everybody did this. We applied the rule, right? We subtracted. Okay. So the blue right here. Ignore the green for now. So the blue right here is just 2x y to the third minus this, and I went ahead and brought the extra 1/2 down. Over here, when I added this, I went ahead and took the dy dx out, and I have 10y and then minus 3x squared y squared. Okay, and then I'm going to have to divide by this, but again, I need this to be just one term. So I needed, so you can think about it as this over 1, but I needed to have it over 2x to the 1/2. Okay, so now I am going to do what? Right, divide by my Oh, hang on. I'm going to divide by this 10 minus 3x, 10y minus 3x squared y squared. And again, when I keep change flip, let me write that out again. When I keep change flip, you think about this as over 1. So it ends up being 4x to the 3 halves, y to the third minus 3, over 2x to the 1 half, times 1 over 10y times 3x squared y squared. So I get 4x to the 3 halves, y to the third minus 3 over, yeah, these answers are ugly.